Hello and welcome to this video on using properties from theorems about eigenvalues and eigenvectors. So in this video, I'm going to be assuming that you already know how to take a square matrix and find all of its eigenvalues and their corresponding eigenvectors and also the eigenspaces of those eigenvalues, which remember the eigenspace of an eigenvalue is simply the set of all the eigenvectors along with the zero vector. Remember, the zero vector is not an eigenvector. An eigenvector is by definition non-zero. So I'm assuming all those that you know how to do all that. All I'm going to do in this video is put out a couple of theorems, a couple statements about a square matrix and its eigenvalues and eigenvectors, and then go through several examples of some 2x2 and 3x3 matrices and just demonstrate how those theorems, those statements hold true. Right? I'm not providing any proofs for these theorems. Okay, if you'd like to look up proofs for these theorems, please do a little search on your own. But just know that these are true statements. What I'm about to show you, I wouldn't just straight up lie to you. All right. Okay, so here they are. All right, now this is just the first two. Now this is not every possible theorem about eigenvalues and eigenvectors there is. All right, there's plenty more out there. I'm just going to make 5 simple statements, 5 pretty big results, results I would expect you to remember regarding eigenvalues and eigenvectors and eigenspaces for a matrix. All right. So suppose A is an n by n matrix, or a square matrix. Then the following statements are true. All right, the following statements are true. They're not equivalent, right? Don't confuse this with equivalent, right? Just because this one's true doesn't mean that this one will be true, all right? And so on. So the first theorem, the first statement that can be proven true about a square matrix is this. A has at most n distinct or different, right? Different eigenvalues. All right, so if you have a 2x2 matrix, a 2x2 matrix will have at most 2 different eigenvalues. All right. This is where you don't count repeats. A 3x3 will have at most 3 different eigenvalues. Now, if there are any repeats, right, you don't count them twice. So you could have, you can have eigenvalues with multiplicities higher than 1. Just don't count that eigenvalue more than once when you're counting distinct eigenvalues. All right. So A has at most n distinct eigenvalues. The second statement, and again, I'll get to examples after this and we'll go through these statements one by one, seeing which ones apply to certain matrices. Number 2, if A does have n distinct eigenvalues, right? So if you have a 2x2 matrix and you do have 2 different eigenvalues, or a 3x3 matrix and you do have exactly 3 different eigenvalues. If you have a matrix with exactly n different eigenvalues, then the determinant of that matrix will be equal to the product of those eigenvalues. That's a pretty nice result, pretty powerful result there. And I would again recommend that you remember. There's only 5 of these. All right, number 3. This is going to sound a little funky, but like I said, we'll look at some examples in a minute, and I'll show you what this means related to an example. Several examples. All right, so suppose lambda 1, lambda 2, all the way up to lambda k are the k different eigenvalues of A, right? So you can have, again, if A is n by n, you can have up to n different eigenvalues. Suppose there might be, but there might be repeats though, so you don't count. So this k here is less than or equal to n. I should, I'll write this here. K with k less than or equal to n. Right. So suppose I have k distinct eigenvalues of A with eigenspace bases b1, b2 up to bk. So that means that b1 is a set of vectors that form a basis for the eigenspace of lambda 1. B2 is a set of vectors that forms a basis for the eigenspace of lambda 2, and so on. Bk is a set of vectors that forms a basis for the eigenspace of lambda k. And I did talk about how to find eigenspaces in my last video. Again, I'm hoping you watch and are following along, so respectively, right, in order. Then, the set, which is the union, remember this is the union symbol here, this U. The set that is the union of all of these, B1 union, B2 union, B3, and so on. Union. If you basically you're just making a set where you take these bases and put all the vectors in the same set. All right. This set of vectors will be linearly independent. Right, and I'll show you again what I mean, what this all means, all these symbols and whatnot, in several examples coming up. The fourth statement I have here: if the matrix is a triangular matrix, so either upper triangular or lower triangular. Remember, upper triangular meant that every entry below the main diagonal was 0, and so the only non-zero entries are above the main diagonal or on the upper diagonal, upper triangle of the matrix. And lower triangular meant the only non-zero entries were on the lower triangle, right below the main diagonal, so you had zeros above the main diagonal. If A is a triangular matrix, then the eigenvalues of A are simply going to be the diagonal entries, right? Just the numbers on the main diagonal. It's that simple. But again, only if A is triangular. All right, and then the last statement, another pretty powerful one, talking about when a matrix has an inverse. All right, number 5, and this is it. Only these 5 statements, and then we'll talk about some examples. This n by n matrix A is invertible, or non-singular, same meaning. A is invertible if and only if, so that means this goes in both directions. If and only if lambda equals 0 is not an eigenvalue. That means if if 0 is an eigenvalue, then A is not invertible. All right. If 0 is an eigenvalue, then A is not invertible. And if 0 isn't an eigenvalue, then A is invertible. Right? It would have an inverse. Okay, so lots of results there. Now, what I'm going to do is go into some examples. Now, some of these I have shown in previous videos, some recent videos I've put out regarding finding eigenvalues and their corresponding eigenvectors and eigenspaces. So, yeah, and like I said, I'm not going to go into finding these eigenvalues and eigenspaces and eigenvectors. Right? I'm just going to state what they are and say, hey, you verify it. You should be able to figure this out. So my first example, A is a 2 by 2 matrix with columns -2, 1, -7, 6. This matrix has a spectrum, lambda of A, the spectrum of A, which is the set containing the numbers -1 and 5. Now remember, the spectrum of a matrix is simply the set containing the eigenvalues. All right. So right away I'm noticing from statement 1, right? Statement 1 applies here. a square matrix has at most n distinct eigenvalues, and you see here I have two different eigenvalues for this matrix. And it was a 2 by 2 matrix. So it can't have more than 2, and we're seeing that it doesn't have more than 2. It has exactly 2 distinct eigenvalues. Then the next statement will also apply. Statement 2 was, if the matrix has exactly n distinct or n different eigenvalues, then the determinant of that matrix will be equal to the product of the eigenvalues. Let's see if that's true, because this statement 2 does apply. All right, this is a 2 by 2 matrix. It does have exactly 2 distinct eigenvalues, 2 different eigenvalues. So therefore, the determinant of this matrix should be equal to the product of those eigenvalues. Should be -5. Well, let's check. Let's check that. What's the determinant of this matrix? The determinant of, -2, 1, -7, 6. Now, it's just a 2 by 2. So it's very easy, this, cross product minus cross product here. That's -12, right? -2 times 6 minus, and then -7. Well, that's -12 plus 7. Hey, look. That is -5. Wow. Okay, so if a 2 by 2 matrix has exactly 2 different eigenvalues, the determinant of that matrix will be equal to the product of the eigenvalues. Good. And again, that applies to any size square matrix, but we're seeing specifically here a 2 by 2. Now the third statement has to do with the eigenspaces, right? Remember the third statement I have here. Suppose lambda 1, lambda 2 up to this is lambda 1, -1, and this is, say, lambda 2, the positive 5. Remember the eigenspaces of an eigenvalue. It's all the eigenvectors along with the 0 vector, right? So, and again, I've done this before on a previous video. You can verify this for yourself if you wish. I'm not going into this. You should know how to do this by now. Right. The eigenspace for lambda equals -1 is the span of the set with the vector -7, 1 in it. So every scalar multiple of -7, 1, except for 0, 0, is an eigenvector corresponding to -1. And our basis for that first set, right, I'll call it B1. A basis for this vector space is just this set with the vector -7, 1 in it. Okay, this is a basis for that first eigenspace. Then the eigenspace for lambda equals 5 is the span of the set with the vector -1, 1 in it, right? So every scalar multiple of -1, 1, except the 0 vector, is an eigenvector corresponding to lambda equals 5. All right, and then hopefully it's obvious to see that this set, I've written them in a way so it's easy to see the basis for the space. A basis for this eigenspace is the set with the vector -1, 1 in it. Okay, so there's all the bases of every single eigenspace, of all the eigenvalues of this matrix. Now, according to this statement, the set that is the union of these bases of the eigenspaces, will be linearly independent. So let's make this new set, which is basis 1 in union with basis 2. So that would be the set. Now remember, if you're in the union, that just means you're in one set or the other set or both. So you're really just taking the vectors from B1 with the vectors from B2 and putting them in the same set. So I've got B1 has the vector negative 7, 1 in it. B2 has the vector negative 1, 1 in it. All right, and this is that set that was being talked about right here, right, where I say B is like the union of all these bases of the eigenspaces. And you can check real quickly this one. This is a set that is, these vectors are linearly independent. Remember, when there's only two vectors, if they're not scalar multiples of each other, then they're independent. And I can't multiply these by scalars to get one another. So this set here is linearly independent, as was stated in statement 3 on the first couple pages. Remember, another way to show this too was to make a matrix with these as columns and then put it in reduced row echelon form. And if each column in echelon form was a pivot column, then the vectors were independent, and that would happen here. In fact, if you made a 2 by 2 matrix with these column vectors, put it in reduced echelon form, it would be the identity matrix. Every column would be a pivot column. And you can double check that on your own if you wish. Now, so far I've worked with the first 3 statements. Right? Now statement 4 does not apply here. Because statement 4 starts off with the hypothesis that A is a triangular matrix. This particular matrix that I'm given here, this A, this is not triangular. It's not upper triangular, it's not lower triangular. Okay, so statement 4 does not apply. All right. Do not, notice that the eigenvalues are not the diagonal entries, right? Negative 2 and 6 are not the eigenvalues here. It's only for triangular matrices where you're guaranteed that the diagonal entries are going to be the eigenvalues. And finally, the 5th statement. Let's see. 5th statement, remember, says that A is invertible if and only if 0 is not an eigenvalue. So we look back here, right, look at the spectrum, and I notice that 0 is not an eigenvalue. All right. Therefore, this matrix A, this 2 by 2, is non-singular or is invertible. And you should be able to find the inverse. And again, it's a 2 by 2, pretty simple. In fact, the inverse here would be negative 1/5 times this matrix here. And you can double check that if you wish. Multiply this by matrix A and you'd get the identity. But I don't care about finding this, so I'm just doing this for the first example. But just know that the inverse exists, right? Since 0, we're seeing that 0 is not an eigenvalue. All right, great. So that's me running through those 5 statements with this, and showing you that for the statements that do apply, 1, 2, 3, and 5, we did get those were true for this particular matrix. All right. My next example, another 2 by 2 matrix, very similar. Okay, this is another one I had up in a previous video. This 2 by 2 matrix 4, -10, -1, -5 for columns. And again, this I have found the eigenvalues already, right? So the spectrum of A is -6 and 5. So notice statement 1 is true. Right? It's a 2 by 2 and it has at most 2 distinct eigenvalues. In fact, it does have 2 distinct eigenvalues. Right? So I mean, it could have 2 or 1, right? But at most 2. Can't have more than 2. So it does have 2 distinct eigenvalues. It's a 2 by 2 matrix. Right? Great. And also, statement 2 would apply, right? Because this matrix has exactly 2, right? It's a 2 by 2 and does have 2 distinct eigenvalues. So remember, like the last one, the last example, it has 2 distinct eigenvalues and it's a 2 by 2, so the determinant of this matrix must be equal then to the product of the eigenvalues of the matrix, -6 times 5, which is -30. And let's double check that. Let's see if I have this 2 by 2. Alright, this would be a -20, then minus, and then 10. And that is indeed -30, which is the same as the product of those 2 distinct eigenvalues. Wonderful. Alright, third statement, remember, had to do with the eigenspaces for the eigenvalues. So here there are 2 eigenvalues, -6 and 5. Again, please, you should be able to find the eigenvectors and therefore the eigenspaces of every eigenvalue. I'm not going to do that here. I've found them already. The eigenspace for lambda equals -6 is the span of the set with the vector 110. All right, so every eigenvector corresponding to -6 is a multiple of 110, except for the 0 vector. Right. Same thing goes for the lambda equals 5. For the eigenspace for the eigenvalue 5 is the span of the set with the vector -1, 1. So every eigenvector corresponding to 5 is a multiple of -1, 1, just not including the 0 vector. Right, so again, what statement 3 is about is the following. Take the bases for this, right? So again, basis, I'll call B1 basis 1. The basis for this eigenspace is clearly the set with the vector 110 in it. And I'll call the basis for this second eigenspace B2. And again, it's clear, I've set them up so it's easy to see. It's clearly the set with the vector -1, 1 in it. And then if I form the union of those bases, the union of the bases of the eigenspaces, I'm just getting the set with the vectors 110 and -1, 1. And according to that third statement I made at the beginning of the video, the third theorem about eigenvalues and eigenvectors, this set of vectors should be linearly independent. And it is. This is another one where there's only 2 of them. And if there are only 2 vectors in the set, if they're not scalar multiples, which these aren't, the set is linearly independent. So it's very easy to check that that is true here. Okay. All right, now statement 4, again, does not apply. Statement 4 only applies if A is a triangular matrix, upper or lower, or diagonal. Right? So again, I'm noticing that this is not. My last example in the video is a triangular matrix, so we'll use it at least once. But this matrix is not triangular. All right, and notice that the conclusion of statement 4 wouldn't hold anyway, right? This doesn't matter. It's not triangular. It says, if A is a triangular matrix, then the eigenvalues of A are the diagonal entries. Well, look at these diagonal entries are 4 and -5. The eigenvalues are not 4 and -5 here. Now there may be some non-triangular matrices out there where the eigenvalues are the diagonal entries, right? That might accidentally happen sometimes, but not in general, as you're seeing here. Right? And then finally, the fifth statement for this. Again, A is invertible if and only if 0 is not an eigenvalue. So I'm saying in the spectrum up here that it's clear that 0 is not an eigenvalue or not in the spectrum. So A is, again, invertible. And you can find its inverse, and again, that'd be pretty easy to find here. It's only a 2 by 2. Great. Next example. Alright, so for the rest of the video, I'm going to be working with 3 by 3 matrices, and just know that the same statements would apply to 4 by 4s and 5 by 5s and larger size square matrices. Alright, so here is a 3 by 3 matrix. Again, I have found the eigenvalues and corresponding eigenvectors and eigenspaces already. You can do that on your own if you wish. So, this time, 3 by 3 matrix. 3 by 3 matrix. So it should have, according to the first statement, should have at most 3 different eigenvalues. And it does. It has 2 different eigenvalues, 0 and 2, 2 distinct eigenvalues. Now this is a 3 by 3. So a 3 by 3 matrix will have, maybe 3, maybe 2, maybe 1, different eigenvalues. Okay. So notice here that it has less than 3 though, right? It has less than n, right? N in this case is 3. So statement 2 doesn't apply. Statement 2 is about, it starts off with if A has n, exactly n distinct eigenvalues. So this is a 3 by 3 matrix, so n is 3. Then the determinant of A will be equal to the product of the eigenvalues. Statement 2 does not apply, right? 2 is not equal to 3. So statement 2 that I had earlier does not apply. Now that doesn't mean, that doesn't mean that the product of the eigenvalues isn't the determinant. It still could be. It's just not guaranteed. Right? It's just not guaranteed. According to this statement, if the matrix has exactly n different eigenvalues, then you're guaranteed that the determinant of A is equal to the product of the eigenvalues. If that's not the case, then maybe, I'll write this, then maybe the determinant of A equals the product of the eigenvalues. But it's not guaranteed like when statement 2 applies, when you have the same, when you have, if you have a 3 by 3 and you have 3 distinct eigenvalues, then it's guaranteed. Let's see. What is the product of the eigenvalues? Let's look at the right side here. The product of the eigenvalues is 0. And what is the determinant of A? Now, if you look at, you can do a cofactor expansion down a row or a column, but one thing I'm noticing right away is that the third column and second column are scalar multiples of each other, right? The third column times 2 would be the second column. So this is linear. These three vectors, these three columns are dependent, meaning the inverse wouldn't exist and all that. The determinant would be 0. So, hey, they are the same, but again, that's not always happening, all right? I said it might happen. Here it happened to work out. For this particular example, the determinant of my matrix was equal to the product of the eigenvalues. But just know that it might not be that case, and I'll show you in the next example actually. Again, where it might not work out. The only time you're one more time. The only time you're guaranteed that the determinant is equal to the product of the eigenvalues is when there's the same number of different eigenvalues as there are rows and columns. 3, 3, 3, and 3 there. Okay. And statement 3 has to do with those eigenspaces again, right? This one here about the union of the bases of the eigenspaces being linearly independent. So I have the eigenspaces stated again. And again, you can find these on your own, please. So the eigenspace for the eigenvalue of 0 is the span of the set with the vector 0, negative 1, 2. All right, so that means every multiple of 0, negative 1, 2 is an eigenvector of lambda equals 0, except for the 0 vector itself. Right, the 0 vector itself is not an eigenvector, but it does belong to the eigenspace. Don't forget that. And then the eigenspace for lambda equals 2 is the span of the vector 0, 1, 0. So every non-zero multiple of 0, 1, 0 is an eigenvector of 2. And again, you just pop in the 0 vector, and then you've got the eigenspace. All right, so the bases, right, B1. The basis for this first eigenspace is just the set with the vector 0, negative 1, 2. And B2, the basis, a basis for this second eigenspace, the set with the vector 0, 1, 0. And if you take a look at their union, it's the set with just these two vectors in it, 0, negative 1, 2, and 0, 1, 0. And one more time, there's only two of them. They're not scalar multiples of each other, so this is linearly independent, as was stated in statement 3 earlier in the video. I'll just write independent. Remember, another way to check is to make a matrix where these are columns. Put that matrix into reduced echelon form or echelon form, and if each column is a pivot column, then all the column vectors of the original matrix were independent, and you can do that too. All right, then statement 4 again does not apply. It says it only applies if A is triangular. Once again, this is not a triangular matrix. Right? Because you got non-zero entries above and below the main diagonal, right? For a triangular matrix, you can only have non-zero entries, above, or all below, or neither. I mean, it could just be a diagonal matrix as well. All right, so statement 4 doesn't apply, and then statement 5, again, the matrix is invertible if and only if 0 is not an eigenvalue. Oh, look here. I'm seeing that 0 is an eigenvalue. And as we saw earlier, the determinant of the matrix was 0. All right, so the A is not invertible. All right, A is singular. All right. Okay. Next example. Again, I've already found the eigenvalues and corresponding eigenvectors and eigenspaces for this 3 by 3 matrix. All right, so and this 3 by 3 here, you find it on your own, has this spectrum, has these eigenvalues 1 and 2. So notice, it's a 3 by 3 matrix. So according to statement 1, should have at most three different eigenvalues. So this has 2, meaning one of these were a repeat. In fact, the number 2 was an eigenvalue with a multiplicity of 2, and you can check that on your own by finding the characteristic equation for A, trying to solve it. But I have 2 different eigenvalues, 2 distinct eigenvalues. And you should have 3 or less, right? Because it's a 3 by 3, so that's true. Right? It's a 3 by 3, and it has at most 3 different eigenvalues. Statement 2 does not apply. Again, statement 2 is starts off with if A has exactly n distinct eigenvalues, and this is a 3 by 3 matrix here, so n is 3. This does not have 3 different eigenvalues. So yet again, statement 2 does not apply. So we're not guaranteed that the determinant of the matrix is equal to the product of the eigenvalues. All right. So let's see what the determinant of this matrix is. Now you could do the thing where I'm just going to go down. It's not a nice one like the last one where there's columns that were multiples of other columns and whatnot. The determinant of this matrix is, I'm going to go cofactor expansion down the first column here. So, the determinant of A is equal to, never mind the 0, and then -1 is in an odd position. All right, first row, second row, first column, 2 plus 1 is 3, that's odd. So when you talk about, you do -1 times the minor, it'll be the cofactor, it'll be the opposite of the minor. So I'll have +1 then times the minor, and then get rid of that, with -4, 2, -6, and 5 like that. And then +1 times, plus, again, down the first column here, +1 times the cofactor would just be the minor this time because that's an even position. -4, 0, -6, -3. Pardon me, sorry, my dog is barking a bit. Okay, sorry about that. And then going through these, this is a -20 plus 12. So it'd be -8 plus, and then 1 times, and then 12. Plus 12 would be +4. Right, and then the product of these, now if you only took the product of these two, you see where it would come across. The product of the distinct eigenvalues. The product of the distinct eigenvalues is not the determinant. It's 1 times 2, which is 2, and these are not the same this time. All right. So last time it worked out, the last example, but this time it doesn't, where hey, the number of different eigenvalues isn't the same as the number of rows or the number of columns in A, so then the determinant of the matrix, may or may not be the same as the product of those different eigenvalues. Now, if you were to actually multiply in this particular case, if you were actually to multiply the 3 eigenvalues that you came up with, 1 and then the repeat, 1 and then 2 and 2, 1 times 2 times 2, you'd get 4. And again, the only reason for that happening is because of the number of eigenvectors in the bases. There are 3 of them of the eigenspaces, and there's a correct number of it has something to do with the number of eigenvectors that show up in the bases of the eigenspaces. That'll be a more general result as to when the determinant of a matrix will be equal to the product of its eigenvalues. All right, and I'm not going to get into that. Okay. All right, so that was statement 2. Again, statement 2 did not apply here because this matrix did not have n distinct eigenvalues, right? It didn't have 3 different eigenvalues. All right, then for statement 3, again, it has to do with those bases of the eigenspaces and then their union being linearly independent. All right, so I've got the eigenspaces. The eigenspace for the lambda equals 1 is the span of the vector -2, -1, 1. Right, so every multiple of this vector except for the 0 vector is an eigenvector of 1. And then the eigenspace for lambda equals 2 is the span of these 2 vectors. Hey, it's got dimension 2 now. The vector is -2, 1, 0, -3, 0, 1. So every linear combination of these 2, right, some number times this plus some number times that, as long as those numbers aren't both 0, right, as long as you're not getting the 0 vector, you'll have an eigenvector of 2. Right. So again, this instead of rewriting all this stuff, this is B1 then, right? Just the set with the vector is the basis for the eigenspace. And then just the set with the vectors, not the span, but just the set with the vectors is the basis for the eigenspace B2. And then I take their union, right? The union of all these bases of the eigenspaces. And then I have the set with -2, -1, 1, -2, 1, 0, and -3, 0, 1. Now there's more than 2 of them, so you can't just check if they're scalar multiples. You have to see if none of these, are any one of these a linear combination of the other 2? And the answer is no. These are linearly independent. And again, a very quick way to check is make a matrix with these as columns, put it into an echelon form, and if each column in echelon form has a pivot, then the 3 original vectors, column vectors, were independent. And that would happen here. In fact, if you double check me, you can try it out. Make a 3x3 matrix with these columns, and you'll see in reduced echelon form, it'll be a row equivalent to the identity matrix. All 3 columns have a pivot. All right. Again, you can verify that on your own, but I'm just telling you, based on what statement 3 is saying, I shouldn't have to check, right? If these are made up of the union of bases of eigenspaces for eigenvalues of a vector, this should be an independent set, and I wouldn't have to check it, right, based on statement 3. Again, statement 4 does not apply. A is not triangular, right? I'll write that again. This is not a triangular matrix. So I cannot apply statement 4. And finally, statement 5, the matrix is invertible if and only if 0 is not an eigenvalue. Well, look, there are 1 and 2, right? 0 is not an eigenvalue. So this matrix is invertible. Wonderful. And you can find it. I'm not going to find it. All right. All right. And my very last example, another 3x3. And let me show you this one before I even get to statement 4. This one is triangular. Look, see, here's the main diagonal. And you see how there's all zeros above the main diagonal, so the only non-zero entries are either on the main diagonal or below. This is called lower triangular. See how the lower, if you break the square into two triangles, an upper triangle and lower triangle, the lower triangle is the only one that contains any non-zero values. So this is lower triangular. So statement 4 would apply. And statement 4, let me just jump to it now since I pointed it out. If A is a triangular matrix, then the eigenvalues of A are simply the diagonal entries. Those entries down the main diagonal, and I've written that over here. See, the diagonal entries are 2, 1, -3. Those are the values in the spectrum: 2, 1, -3, -3, 1, 2. And you can verify this the other way if you want. Set up the characteristic equation. And if you remember that the determinant of a triangular matrix was just the product of the diagonal entries, right? So the determinant of this matrix would be -6. If you remember that the determinant of a triangular matrix is the product of the diagonal entries, you'll see very quickly when you go to set up the characteristic equation that the three diagonal entries, 2, 1, and -3, have to be the eigenvalues. All right, so statement 4 I've already applied. All right, if it's a triangular matrix like this is, the eigenvalues are the diagonal entries. Simple as that. All right, so back to statement 1. Now this is again a 3 by 3, so it should have at most 3 different eigenvalues, which it has. All right. And this time it actually does have, the last two examples, there were only two distinct eigenvalues. This one does have 3 distinct eigenvalues, -3, 1, and 2. So now statement 2 is applying again, right? If the matrix does have n, right, 3 by 3, so 3, if the matrix has 3, in this case, different eigenvalues, then the determinant of A is equal to the product of the eigenvalues. So the determinant of this matrix should be, -3 times 1 times 2, or -6. And that is true, right, in this case. Remember I said earlier, if you have a triangular matrix, lower triangular, upper triangular, or diagonal, the determinant of that matrix will simply be the product of the diagonal entries, so 2 times 1 times -6. So that is working out for this one as well. Statement 3 was about those bases, right? So again, I'll call just the set, the eigenspace for -3 is the span of the vector 0, 0, 1. The eigenspace for lambda equals 1 is the span of the vector 0, 4, 3. And the eigenspace of lambda equals 2 is the span of the set with the vector 5, -5, and 2. So again, I'll call it just the set, not the span, but just this set is basis 1, just this set basis 2, and just this set with 5, -5, and 2 basis 3, the bases of all these eigenspaces. And again, you can find these on your own. I'm not going into that. Well, according to statement 3, their union, B1, union, B2, union, B3, which is simply the set with all these vectors in it, right? 0, 0, 1, all these basis vectors, 0, 4, 3, and 5, -5, 2. This is a linearly independent set. These are all independent vectors. And again, there's more than 2 of them, so you'd have to check more than just are they scalar multiples. Again, if you were to make a 3 by 3 matrix with these as columns, all right, I hope you can see that it would be row equivalent to the identity matrix. All right, I really hope you can see that. All right. In fact, if you switch it around, if you put this vector first and this vector last, it wouldn't matter. You'd get a lower triangular matrix, and a lower triangular matrix is definitely row equivalent to the identity matrix. So all three, when you put this in a matrix with these three columns into echelon form, all three columns will be a pivot column, so all three of these vectors are independent. All right, you can't write any one of them as a linear combination of the others, so these are independent. And again, I shouldn't have had to check that, right? If statement 3 is really true, then the union of the bases of these eigenspaces for the eigenvalues of matrix A, the union of these bases should be a set of linearly independent vectors. All right, I've already applied statement 4, right? It's a triangular matrix. The entries on the main diagonal and the diagonal are the eigenvalues. Cool. And then statement 5 is that the matrix is invertible if and only if 0 is not an eigenvalue. And again, I am saying 0 is not in the spectrum. Right? It's not an eigenvalue of this matrix. So this matrix is, again, invertible. Right? And you can find the inverse, and again, I'm not going to go into that right now, finding the inverse. Wonderful. Okay, so once again, the 5 statements, all right, to finish the video with as well. So 1, well, again, these are all about square matrices, some n by n matrix. 1, the matrix will have at most n different eigenvalues, right? Some may repeat, but you don't count repeats more than once when you're writing them in the spectrum. 2, if the matrix has exactly n distinct eigenvalues and different eigenvalues, then the determinant of the matrix will be equal to the product of the eigenvalues. Number 3, if the matrix has eigenvalues lambda 1, different eigenvalues lambda 1 through lambda k, where k is less than or equal to n, if lambda 1, lambda 2 up to lambda k are the k different or distinct eigenvalues of A with eigenspace bases b1 through bk, respectively, then the set, which is the union of those bases, will be linearly independent. 4, if A is a triangular matrix, upper or lower or diagonal, then the eigenvalues of A are simply going to be the diagonal entries of the matrix. And then finally, 5 again, if A is invertible, if and only if, right? Lambda equals 0 is not an eigenvalue, right? So if 0 is not an eigenvalue, it's invertible. If 0 is an eigenvalue, it's not invertible. Simple as that. All right, so I hope you keep those in mind, right? Those important properties, theorems about matrices, and their eigenvalues and eigenvectors. Keep those in your head when you're looking at matrices and their spectra, and also the sets of eigenvectors and the eigenspaces corresponding to certain eigenvalues. Right. And thank you very much for watching.